Perfect. Well, thanks a lot, everybody, for offering this chance to present. Hopefully, everyone can get to learn something. I know there's a lot of expert audience, and I tried to, like my best to give some value to everybody who's here listening today. So I'm just going to go ahead and share my screen so then we can get started. So I chose this competition. It's Don't Overfit. And today I will be talking a little bit about my motivation to do this presentation and what my expectation versus my experience was. And the competition overview, of course, and the exploratory data analysis, feature selection, and model validation and overview. So my motivation for this was, it was a really good opportunity for me to learn and grow because I have a background in data visualization and database and manipulating the data, but I never had a step into the machine learning side of things or the AI side of things. So it was a really nice opportunity. And also it's a really friendly environment. I just started joining this group back in February. I think this is probably my 4th or 5th week. And also the peers over here are really supportive. So anybody who's new here, I think you guys are really gonna like it here. And also, last point is, it's a nice challenge. Like, you know, I took this presentation and I knew it was gonna be a little bit hard, but it was more harder than I expected it to be. But in this process, I definitely learned a lot. So my expectations were I had like 3 weeks of time when I finalized this project and this competition. So I was like, oh, I have a lot of time. Like, you know, I'm gonna go in depth and everything, and I'm gonna like, you know, do like a whole exploration of the data and do all the analysis. It's gonna be great. But it turns out, like, you know, with jobs and other responsibilities and everything, I only get to put in about like 40 to 50 hours. And also my expectation was that there's going to be a lot of intense mathematical and statistical background, which we'll need to optimize the algorithm. But it turns out when I started to work, and it was more because I'm a software engineer, so I have more experience with Python. It turns out that, you know, using Python algorithms and you know, tweaking their parameters and you know, measuring the output is a lot more handier way to get started than just to learn all the mathematical backgrounds. It's good to know, but I didn't get a chance to apply those mathematical knowledge or statistical knowledge much in this competition, which I learned. And my main expectation was that the data will speak, that, you know, once I will visualize the data, once I will look at the data, I'm sure I will find some patterns and I will use it to predict. But sometimes it doesn't translate to a useful value. And also, it's good to research everything online and find everything on Google. There's a lot of articles and peer-reviewed studies. But I think really helpful to me was reaching out to Bruce and Matt and Stephen. And their advice was like, you know, a lot. It saved me a lot of time. You know, I didn't have to go to research and all that stuff. So, and also my expectation was not to overfit, but after doing this competition, it was really hard. the data, it's really hard not to overfit. So the competition, the model is 20,000 into 200 metrics of continuous variable, and the data set is only 250 samples. And you have to create a model without overfitting, which gives you a really high prediction score. So the top of the board were these are the scores of the top 10. I think the 10 score, the 10th is 0.864. I'm not sure if these are public or private. Or maybe someone can mention that, because I did run a bunch of stuff and I wasn't sure which one gets shared. But after from 10 to 17, the score remains the same. And these are the best scoring notebooks. I didn't look into all of them because some of them are in R, and I didn't have a lot of experience with R, so I looked more into the Python notebooks. So I went to the most voted notebooks, and I chose these three. Also, number third one was LB probing strategies. I believe that's leaderboard probing strategies. I'm not too. He used random data to work his hypothesis there, so I couldn't follow up with him very much. But the fun data animation one, which is I believe the 1, 2, 3, 4, 5, it's a really good. If anybody wants to sort of create a GIF from the data, like and rotating at different angles, that was really nice. So these are the three main notebooks I explored, and I will talk about it in this presentation today.
Hey, RJ, just to confirm, yeah, that LB probing, that is leaderboard probing, and typically what they do is they'll just come up with some way to randomize the outputs of their predictions, and then they'll submit a whole bunch of times to the leaderboard. Every time they submit, they'll get that public score back, and essentially he's just trying to figure out how to maximize that public score. And then and then he'll in the private score he'll probably fall down like to last place or something.
Okay.
It's really just about to optimize for that public leaderboard score.
Okay.
Yeah, it's not a good technique. You can kind of feel good because you go up the leaderboard because you're kind of adjusting your results for that, but they separate out this public leaderboard from the private, and the private's against data that you don't get to test against until the end. And it's very easy to overfit to the public leaderboard, and then it doesn't work on the private one. So it's not a recommended technique by any means.
Okay, that's good to know. So training data had 300 features, 250 training samples. There were no missing values, thank God. And the test data had about 19,000 samples. So as you can see, the training set is really tiny as compared to the test set. This is my first Kaggle competition, so I'm not sure if that's the standard way of how the data is distributed. And the target, the label is binary classification. So the count, which you guys see, the 0 and 1 is the 250 samples count, where I think the 0 is about 180-ish, and then the 1 is around 60 to 70. Yeah.
I will comment in terms of the number of training samples. That is actually very small. Usually, you've got thousands, sometimes even tens or hundreds of thousands of training samples. But they're specifically setting it up this way so that you can get experience of techniques when you don't have very much data.
There's also, that ratio is also very off. It's more common to have more samples in the training set than it is in the test set.
Yeah, it was a little bit, it was interesting, I guess. So first I started looking at from the basics, started looking at all the standard deviations and the means. So this is the distribution of the data. I saw it was more or less of a bell curve. And then we started doing the exploratory data analysis, look at the number of unique values, and these are the first 28 columns histogram. Most of the values do fall between -3 to 3 or -2 to 2. But I guess. So yeah.
Sorry, RJ, I'm a bit confused. Yeah. Is it continuous data?
Yes, it is.
But then there were so the number of unique. Can you go back one slide? Okay, and then there were 250 samples in total, and so there are a few cases where there were a few duplicates in one column. This is what this is showing, but it doesn't happen very many times. Yes,
I'm going to talk about this later as well in my next slide.
Oh, okay.
But yeah.
Oh, sorry.
So I tried to find the correlation. It was really low between all the variables. This is just the first 3 variables, and just trying to do a scatter plot between all the other 299 variables. So I didn't find a sort of a plane or any linear fit to these correlations. And then I also tried PCA. So the first image is rotating at a 0-degree angle, and the second image is rotating on y-axis, and the third image is rotating at a 30-degree angle. So this was more to see if there's sort of a hyperplane I could find where it kind of distinguishes the 0 and 1. But also, by the way, this is all the 300 columns. And so I just tried all these models with default setting on all columns just to see where the base is. So these are my public and private scores. So the LGM regressor gave me the highest private and public score with the default setting with all 300 columns. And then the Bernoulli naive bias gave me also the similar kind of public score. I think I wrote it wrong. I think they're opposite. I think the public is private and the private is public. But yeah, these are my base. I just tried a bunch of different algorithms to see how it would work if I just throw in the data to make the prediction.
Hey, a couple comments here. So one, do you happen to know how the data was generated? Was the data generated specifically to make it hard to develop models?
Yeah, I believe so, because I tried a lot of different techniques, and it's literally to make you kind of hurt yourself. Yeah, the data is very diverse, and there's not a lot of correlations. And I try visualizing it, and even when you look at the correlation between the different algorithms and models, and what are the top features, and kind of like use them, like I nothing really much changed, to be honest. Even after trying all the strategies in those notebooks, my score didn't pass this 0.25 and this 0.5.05. So this is still like the max score even after trying all the strategies they mentioned. I think what happened is they changed the data, most likely, or maybe because when I was looking at some of their notebooks and some of their outputs of the data, my outputs weren't the same. My top features were different. And a lot of I have a little bit of, my data was different than their output. So I think they might have changed the data. I'm not sure.
Were they doing any, they must be doing a train test split, and then they would have were there any random seeds maybe that you missed that?
I used the exact same random seed values as mentioned in the notebooks. So that's why I was a little bit like, did they change the data? But again, I'm a very beginner. I could have made a mistake somewhere, which I have not found yet. But yeah, hopefully you guys can find the mistake and let me know throughout this presentation.
Do you have your code available?
Yeah, I actually have a lot of code. I was working on it up till the very last minute. So I think some of the visualization I kind of missed to put in the presentation, because I just was working till 5:59, and then I was like, okay, this is done.
Just like me, RJ. Just like me. Bruce. Oh, sorry, Bruce. Did you have a comment there? I have one more comment on the slide, but I'll wait.
No, I thought better of my comment. You go ahead, Matt.
Okay, I just wanted to point out there's a lot of different models you have here, and I know at least the cat boost requires its own custom way of feeding the data in and out. And how did you select all of these different models, and did you find it useful to kind of go through these examples? Just curious on your experience.
So in the notebooks, there were pre-made functions. So they kind of like they have like different if statements and switch statements. So where you kind of, when you choose a certain model, then it will process it differently. That's what I really like from the notebooks. They pass in the parameters and stuff, but I just ran everything in default setting without passing any parameters, just because I want to see that how this works at the baseline without changing anything at all.
Okay, cool.
So then I used the correlation feature to see what are the most top 5 correlated features. As you can see in the first table. So you can see the correlation is not that high. I was expecting to have a correlation more than 0.5 from my one machine learning class I took. I had learned that it's good to have a correlation more than 0.5. But as you can see there, these are the top 5 correlated features I could find, in the data, and they're all 0.3, 0.2. And on the right-hand side, there is the permutation importance library I used with linear regression to kind of find out the most weighted features. So I believe there are like the top 30-ish features. And then these are used later on, again, in the algorithms this time. This time I'm running the algorithms with these top features instead of all 300. And also, by the way,
sorry, RJ, quick point there.
Yeah.
So you mentioned linear regression. This seems like a problem that would be more suited to a logistic regression. It's a classification.
Oh yes, sorry. It is logistic regression.
Okay, great.
Yeah, and also at the bottom I have the source of the notebooks from which I'm following. So these notebooks have a lot more explanation and in-depth analysis. I just used whatever I could understand. So then I also used a shape value, which is a game theory approach. Also, it's also calculated on logistic regression. So it is to kind of find out the importance of the top feature selected in the permutation importance. So as you guys can see in the image on the right, feature 332751 shows some impact, whereas the other ones are kind of like no impact, I believe. I also was kind of trying to understand this graph, if it's more if a feature is more dispersed linearly, I guess it has more impact.
Sorry, did you say this was done with a logistic regression model, and you produced SHAP values from that? So for logistic regression, the SHAP values are going to be equal to the coefficient multiplied by the value of the variable.
Okay, the coefficient multiplied
so you could basically get the same information just by looking at the coefficients.
Oh, like as in the table on the right here?
Yeah.
Okay. I was following what was done in the notebook.
It's a bit of a strange thing to do, at least so SHAP values make a lot of sense in terms of like other models, because there's usually no like readily available, easily interpretable like model of them. But in the case of linear and logistic models, the coefficients, well, as I said, like the SHAP values are sort of like a generalized coefficient for other kinds of models.
Okay, that's good to know. Yeah, and then I use a sequential feature selector on these top features to kind of see the performance, which didn't change much after the second one. It's kind of steady. And I use the scoring ROC, AUC. I think it's under the curve for, I forgot, I did look it up. And yeah, and these are the cross-validation scores comparison with stratified k-fold. And as you guys can see, I'm I was trying to understand how to manipulate these box plots. So I believe here the best ones were the logistic regression, and yeah. Can you guys help me interpret this?
Hey, can you go back one slide, please?
Yeah, for sure.
So on your left-hand side, you say scoring ROC, and you gave chart, number of feature.
Yeah.
So is that ROC chart? Because ROC is 0 to 1. It's like,
Yeah, I think it's
one.
he's adjusting how many features he's going to be using in his model. Is that right, RJ? So you're saying
Yeah.
we're going to have a model that's trained with just that feature 33, which is the most important one. That gives us an ROC score of 0.63 or abouts. And then if we use two features, or we use feature 27 and 33 into a model, then we get a score of a little over 0.65. And ROC is just the metric that we're using. Is that right?
Yeah.
Okay.
And ROC AUC stands for receive operator characteristic area under the curve.
Right.
Just correct.
Yep.
On the next slide, RJ, I can try helping you out here. So this is this a cross-validation score?
Yeah,
that
the
what you said?
cross-validation score with the top features.
Okay, so what we're doing is we're using 20 splits. So we're gonna do 20. We're gonna train 20 different models where we've split the data so that there's 5% each time that's going to be left out as our validation set or our test set, and then we're going to use the rest to train, and then we're going to score it on those 5. It's probably not that many. It might be too much of a split in this case because we have so few samples to begin with that we have really a very few samples in each of those validation sets. But
it amounts to it's 250 in each set, right? So that means 12.5, I guess.
Yeah.
So 12 or 13.
Yeah, so some will have 12, some will have 13, I guess. And so what this is saying is we're going to take those scores in the validation set. We're going to take all 20 of them. We're just going to average those, and then, or we're not going to. I mean, we're just going to plot all of those scores in this box plot. And so, a logistic regression actually looks like it's doing pretty well.
Yeah.
Just a small question. Are you using all the features right now, or you are just using the top features?
No, this is using these features mentioned on the right table here.
Okay. And till now, we haven't done any pre-processing. It's just the raw data, right?
Well, it was already pre-processed. The data was kind of normalized. Yeah, there was no missing values. I didn't have to, when I was doing my visualizations and all the standard deviations and mean, I didn't see any sort of discrepancy to kind of scale the data, that the one feature is really too high and the others are kind of low. I think they were all pretty much scaled.
Yeah, I have a question. Did you look at outliers if you have a lot of outliers?
I did not look at outliers, but I don't think so. There are very many outliers. I think most of the data is close to the mean, which is, I think, 0.
So some of these models would be really affected by outliers, but other ones wouldn't. So like the tree-based methods shouldn't really care about outliers. But it is definitely a good thing to keep in mind as you're using some of these. I would say the feedback here is I would really try using lower number of splits, because typically when you train an algorithm, you are always looking at that validation score to know when to stop the training process. And when you have so few samples in that validation score, I feel like you're not really knowing when you're overfitting on that training set or not. And so you really need to have enough samples in that validation set for the algorithms to really work properly, I think. So even just splitting, I think a typical cross validation just uses 5 splits. And this one you might even want to use 2 or 3. But
okay, that's good to know.
I don't know, but I don't know. I could easily be wrong. One of the things you
Worth
can
a
try
shot.
playing around with.
I'm still gonna play around with it after this presentation to try to get my score higher and see if other techniques work. So yeah, anything. I'm still writing down notes to try it out. Thanks. So then I use polynomial features with 2 degrees. These are with the top correlated columns and model with logistic regression. This one visualization, the top one, took about 20 hours worth of time, which was not expecting it to take that much computation time.
To train a logistic regression model?
With polynomial features, yeah.
How many polynomial? Oh, I mean, still, like, it's regression, right? So, yeah, that is odd.
Also, my computer is 4 GB of RAM, so it's not like a very powerful system.
Yeah, but with 250, like, it's a very small data set.
Yeah.
So that is kind of odd.
So this model, you're essentially taking the feature itself and also a square of that feature if you're using degree 2, and you're saying, okay, well, now I have twice the number of features, and I'm going to fit coefficients to each of those. Is that what this is doing?
Well, no, you can also say, like, if you've got 2 features, then you can multiply the 2 of them by each other. So feature 33 multiplied by feature 5 would be a second degree polynomial.
Yeah.
So
maybe it's the number of permutations of those combinations that led to the long training time.
But there's not actually that many permutations, right? So let's see. Like, if it's just degree 2 and you're using 5, did you said the top 5 features?
No, I think they are using. So this is the code right here. So it takes the polynomial feature degree 2, and then this is the test train, and then this is the loop, which took really long time. So it's
comment above about 45K features, which they didn't do. We need some way to select them.
So this is the top correlated columns taken from the data, and then it trains on these only these top correlated columns, and which produce this.
How many correlated columns were in the top correlated columns in this case? It wasn't 5.
I believe. Let's see. I think I did have this. Let me see. I have to go to my own notebook. I think there were about 35. Not like with the polynomial, I think there could be more.
So 35, if you use 35, then like the most features you can get is 35 times 35 plus 35. What does that equal to? So that's roughly 1,000 features. I don't know where they got the 45K from.
I'm just going to go to my notebook. Yeah, and then the second one is the recursive feature elimination with logistic regression, also using the top correlated columns. I'm just going to double check the top correlated columns and see that how many features there are there.
I just did a bit more math, and I think I figured out where they got the 45K from. That's if you take all 300 features. So that's what they were referring to there.
Okay.
Whereas here, 500 is roughly where it actually tops out.
So it's the 300 features into 300. So that will be
90,000 divided by 2, because that's a skip. It's a step I skipped before. You need to divide it by 2 because it's otherwise you're counting some of the features twice.
Okay.
Because like feature 33 times feature 5 is the same as feature 5 times 33.
Okay.
So they wanted to down select this based on the features that were correlated with each other. Is there a reasoning behind that? Like, why would they want to only multiply features that were correlated with each other?
You'd think you want to multiply features that aren't correlated with
I thought
each
they.
other.
I
Well,
thought
that's
they
what.
were, I'm pretty
Yeah.
sure they meant like the top correlated in terms of like correlated with the target.
Oh, you mean the feature on its own is meaningful. So they're only using those meaningful features.
Yeah.
Or more meaningful features. Okay, that's a better way of interpreting it, I guess.
Yeah. And then after these two, they also used.
Wait, so sorry, RJ.
Yeah.
These CV scores are decent, right? Like they're a lot better than the 0.5. Does this mean that essentially we're just picking up some difference between the training set and the testing set? Did you try submitting like these models that were trained that gave you these CV scores submitted only gave you a 0.5 score?
I did, and yeah, they didn't give me much. I think they were more like 0.5, 15.
Yeah.
But no, I didn't get more. Really, it didn't really make a lot of difference. I did submitted all of these, and there's a few more recommendations after that. I tried those as well, but that's what I was a little bit surprised about. That none of these techniques sort of kind of worked. Even though on the cross validation data set, they did show improvement by some techniques, but when I submit this score with Kaggle, I didn't see a lot of increase. Maybe like 0.005 or 0.010, but that's about it.
So like,
but I think what you said earlier, Matt, I think is the clue to this, right? Isn't it? Like there's so many splits, the validation set's very small. The techniques are kind of overfitting to the validation set if you're using that as your stopping criterion. So it looks better than it really is.
There's also it's also possible that there is actually just some like there's. I mean, there can't be there might be some fundamental difference between the training and the test set in terms of like the distribution, like all of the underlying variables, not necessarily in the distribution of the variables, but the way they relate to each other. Does that make sense?
Yeah, I think I should have also explored the test data quite well, which I believe I didn't, because I think I was focusing all my time just analyzing the training data. I think if I would have looked into the test data, I would have found some similarities or dissimilarities in regards to the training data.
Yeah, like some of the plots that you showed at the very beginning were independent of the target variable, just like the mean and standard deviation and stuff like that. I'd be curious if those lined up with the testing set. It might give you some clue.
Also, whether or not I'd be interested to see whether they like the correlations between all of the features in the training and test sets were similar. Like you might find that some variables are more correlated in the test set than they were in the training set.
Yeah. So, and then next recommendation was to add extra columns. One column for extra as in a standard deviation and one mean column, and then do the same thing again. And then I think the simple CV score and the with mean CV score is the same, because those lines overlap and we don't see them. But what the green one is the with standard deviation. So one data set is just as it is, and just the top features, and then the second data set is top feature plus the standard deviation column, and then the third data was the top feature plus the mean column. And then again, the model was logistic regression, and the weights, the top features are pulled up from EFI weights. And that is the visualization you guys see on the right. And then the second slide is with a repeated stratified k-fold versus stratified k-fold. And yeah, and I believe those CV scores are a lot different. If someone can explain a little bit difference between repeated stratified k-fold and stratified k-fold, that would be amazing.
I'm not familiar with it, but if I were to implement something like that, then I suspect the difference is just that repeated stratified k-fold would be you do the split 20 times using a different random seed each time. So you get 20 different subsets each time. So I mean, I guess that would definitely be more reliable in the sense that it's possible that you just got like a particular, like you group them in a strange way the first time around, but if you do it more times, then it should be more reliable. It's still a little bit odd.
Yeah, so I think David is exactly right, but I'll add a little bit more information as well. So when we say something is stratified, it means that in all of our different sets, we're going to keep the same proportion of classes. So that is like ones and zeros. So it means that in a stratified k-fold, we're of split 20, we're going to be splitting the data into 20 different little bits. So 20 different subsets, and in each of those subsets, we're going to try to maintain the same proportion of ones and zeros in each. That's what the stratified portion means. And then in a typical stratified k-fold, what I said is the case there. So we're going to split our 250 samples into 20 different buckets, and then we're going to do the training where 19 of those buckets will be used for the training and one of the bucket will be used for validation, and we'll do that 20 times for the 20 different training sets. And then I think as David pointed out, I think the repeated stratified k-fold, I don't know about this exactly, but I think I would guess that he is right, where instead of splitting all of the 250 samples into 20 buckets, what we're doing is we're just going to randomly take 5% of these 250, and then that's going to be one of our sets, and then we're going to do a different 5%, and that's going to be another different of our sets. So it doesn't guarantee that you're using every single sample in a testing set, but it does add some element of randomness. And there's actually no reason that you have to do the the amount that you're splitting. Oh, sorry, how am I going to say this? You can do 20 repeated splits, where in each of those splits, you're doing 20% of the data into validation, right? Like there's nothing to say that you have to use only 5% of your data for validation when you're doing this repeated algorithm.
Yeah.
But then again,
if anything, I think I'd be inclined to reduce the number of splits and increase the number of repeats. That's probably more likely to get a reasonable result.
Okay.
Just before we carry on, there's a good question in the chat that I think other people might be wondering as well. I'm not going to attempt to answer this. I'll read it out and I'll leave it to others to suggest answers. But what indicated the need to generate further features if there were already 300 features to train on?
That's a very good question.
I think it's just fun to try all the little tricks of data science and see what works. I think that's essentially the goal here. But I think that's a really good point, Mark. I think that you would really want to exhaust as much as you can from those 300 features for a long time before you convince yourself that you need to combine them in weird ways. Although the mean across the rows, that seems like maybe a good one to throw in there. That's just one extra feature.
There, like a lot of the extra features they use, like the assumption is just that there are a lot of non-linearities in the data set. So this approach makes sense when you're using a linear classifier. It doesn't make so much sense if you're using a tree-based model or something like that, which can already deal with nonlinearities.
Yeah. And
I would say in a weird sort of way, it's an attempt to deal with the large number of features, because there's too many features, and we're just bound to overfit because we don't have enough training data. But if you could find, if you narrow it down to just a couple of features, that may not be a rich enough description for what's going on. But if you can find, like, the ratio of a couple of features or something like that, a small number of things like that describes the data well, then you might accomplish both getting a better result and not overfitting at the same time.
Yeah, one strategy that might work here is coming up with some automated way of generating a whole bunch of features, like thousands and thousands of features, and then throwing it into a model that can handle a lot of nonlinearities, like a decision tree based approach. Because then you might just find some combination of this feature set that just unveils like a magic new feature, and then the decision tree will be able to pull that out very easily. So it's one possible way. It's essentially trying to hack like how they came up with these labels.
That would be a very good way of that would be a very good use of SHAP values there as well. Actually, you could identify the magic feature that was produced quite easily using them in that instance.
Yeah, I think there might be packages that'll do that for you. I've never used them, but I've heard of them. Feature engineering is such a common thing to do in problems like this that I think people have packaged it up into reusable libraries, techniques.
Sorry if I could interrupt, but a couple of slides earlier, we did principal component analysis to reduce the number of dimensions on the data. So that's kind of also a reason why I was slightly confused. So as far as I know, I understand that by combining certain features, you might get a different distribution, but isn't the goal to try to reduce, because as the number of features increase, then it gets harder and harder for the model to understand where those linearities exist or the hyperplane exists that divides the data set. So I thought that was the main goal, is like try to reduce as much as possible the dimensionality in order to understand the real distribution between the two classes.
I think it's a great point. I'll attempt an answer. I'm sure others have things to say too, but PCA will only discover linear relationships between features, and these other techniques like the polynomial techniques are looking for more nonlinear features.
Also, I think I have a strong suspicion that they did some form of PCA when producing this data set, just based on like the distributions.
Yeah, the lack of correlation and the fact that it's normalized, right? Everything's between -2 and 2, and looks like, censored. I suspect it's a very curated data set, I guess.
Yeah.
Thanks.
So that was the end of the first notebook, and now we're starting the second notebook. And I'm leaving all the mutual stuff between the notebooks. I'm only bringing whatever the extra or different things the second notebook person tried. So yeah, this is the second notebook. They tried to use extra tree classifier to find out the top feature importance. And then they use the recursive feature elimination with XGBoost, and they selected about 150 features. And I think they later on smoothed the training data with synthetic minority oversampling techniques. So they kind of pad.
Actually, I was about to ask you, like, why don't you apply that smooth initially, right in the beginning? Because, if your data is imbalanced, right, your accuracy and everything is off. So once you do this synthetic minority oversampling technique, you balance both the labels and then you start from there.
Okay.
Am I right, Matt?
Yeah, actually, that's a great point. That might be why the CV scores were always around 0.7.
Right.
If there was about 70% of the data that was 0 and 30 that was 1, I forget which one had more. But then, yeah, the model just might be always guessing that majority class and essentially is learning nothing except for
Right.
the
Right.
amount of
So
labels. Yeah, that's a
think
good point.
about this way. Say when you do cross validation for 20, you have like 20 or 13 data points in each, right? And the probability of having the label 0, which is minority, is very less, maybe 1 or 2, or maybe less. We don't even know.
Mhm.
So the next step suggested in this notebook was to combine the models. So they're using the logistic regression and XG classifier to kind of like, and they have, I guess, some weights assigned to them. And then I think in the next, oh, I think I didn't. I just wanted to show you guys the quickly the outputted so yeah. So this is from the first. So this is kind of like the weighted prediction. I think this is later on they're using stacking classifier, but I wasn't really sure that how this particular combination will help the model.
It's just they're just trying to ensemble some models together here, I guess.
Yes.
Yeah.
They're doing a weighted ensemble.
Mm-hmm.
They're
So
saying the
there is
first
a
models.
concept.
Oh, sorry, go
There's
for
a
it.
concept called weight balance. So are they doing weight balancing there? Because it looks like PRID, that is a dictionary, and weight PRID is some weight balancing number they calculated somewhere, and they're using it.
Yeah. Yeah, they didn't really mention how these weights came from or where they came from. And they just kind of like had this one.
No, you can see it. You can see it in the formula, right? PRID multiplied by weight and divided by sum. So that is means they're taking like weighted average of that weight and then going ahead.
Okay, I see.
Well, yeah.
So see on the fourth to the third to last, they have weight, which is 1 and 0.3. So that means they're giving more weight to one than another. So that is what weight balancing is.
No, well, I mean, it's just a weighted ensemble, right? So like they're weighting the logistic regression 3 times as much as the XG boosted classifier, roughly.
Okay.
Which seems odd to me. Like I would have. I'm not sure how they came up with those weights. I'm guessing it must have just been trial and error.
It's always it's a bit of a dark art coming up with these weights. Oftentimes I just hear that people just tried different ones and then they found the leaderboard score improved with one as opposed to the other, or that they just had some intuition that like this one model performs better than the other model, and so we're going to count it as more.
No, there is a logic behind this weight. If you look, I mean, think about it. You have minority, which is like 60 or whatever is that, and majority was 165 or whatever is that. So it's like 1 to 3 ratio, right? So this is exactly the same ratio you see it, 1 to 0.3.
But that doesn't explain why the LGB, like why we'd want to weight the output of the logistic regression 3 times as much as the output of the XG boosted regressor, right? So like those are 2 very unrelated issues.
Okay. Yeah, I see where Mo is coming from. He's mentioning about that the weights are
right.
And the difference in the count.
So this is, so if you go to scikit-learn and you Google it like weight balance. So whenever your data set is not balanced, you can put the weight, and this is the technique.
Right,
Okay.
but
One of
what we're using these weights here for is not related to the ratio of the labels.
Yeah, this
Yeah.
has nothing to do with the different classes. This has got to
Right.
do with the different models.
Yeah, this is with the logic regression and XG classifier. Yeah. Okay.
This is something that's probably way beyond where you needed to get to right now. I think the focus for you right now is just to try to get one model to perform well. And then
Yeah.
once you're able to do that, then you can try to get another model to do well, preferably a model that's slightly works in like a slightly different way. And if you can get two models to work well that work in independent ways, then you should try ensembling them together and seeing it'll almost always improve your results if you get two models that work well.
Okay.
As long
So
as the models, ideally the models need to be different in some fundamental way. Like often when they do this ensemble, they're not particularly, but like logistic regression and a tree are different enough so that they will pick up on different things, and it does kind of make sense to ensemble them.
Yep.
Okay. And lastly, they use stacking classifier. So it's kind of the same, but there's no weights here in this one. But they still have a predict parabola, and they, I guess, I am not sure how the stacking classifier works.
yeah, so this isn't even a step even beyond what the step of just doing kind of the weighted ensemble. So this is instead of having those 1 and the 0.3 in terms of defining how we're going to combine these two models together, this is essentially saying, okay, well, we don't want to hard code these values in. Let's just have a model learn how to combine these two models together.
Okay.
And so essentially you're putting a model on top of two different models, where this new model is only ever looking at the outputs of those previous models and is trying to determine the best way of ensembling them together. Yeah, this is something that a lot of winners use to kind of get like a very slight edge upon the rest of the competition and Kaggle competitions, but this is kind of advanced for now, I think.
It also seems a bit like overkill when you've only got two models.
Yeah.
And and then this is the last notebook. And so this got started from getting the unique values from all the different columns. And then this is using gradient boosting machine to find the feature importance. And it's creating this feature importance matrix where all the features are kind of in the order of their importance. And on the right there are the top 15 features with the normalized importance. And then it's suggesting that to get the cumulative of 0.99 cumulative importance, we need about 200 features required. I haven't shared the code of this function, but it is using gradient descent boosting to get the feature importance. And then it removes all the features and then kind of keep around 240 features to match the 0.99 cumulative importance. And then it aggregates the RFE score of these three models, logistic regression, decision tree classifier, and SVC, and then use voting classifier, which I believe is a voting or majority rule classifier for unfitted estimators, and then uses k-fold cross-validation to get the mean score, and then visualize SQL forward selection. So this is kind of like
question. What is that shaded area? Is this confidence level?
Yeah, that's a good question, actually. I am not sure about that.
They said they did, the k-fold cross-validation, that I'm assuming that this is just like the difference of the the standard deviation of the performance of each of the folds.
It says with standard deviation there, so I'd imagine that's what it is. So
Okay.
for number of features 2, we're going to be, I mean, let's just say for the sake that they're using the same, they're using 20 splits again for this one. So they're going to run 20 different models with 2 features. They're going to get a whole bunch of scores. You'll take the mean of those scores. That will be the red dot. The standard deviation, that'll be the gray.
Yeah, got it. Thank you.
So that was it. And in the overview, what pretty much I did was I explore and visualize the data. Then I ran and compare model with basic and default setting. Then I spend some time on data preparation, which is more so feature selection or feature engineering, and trying different things. I tried a lot of different code from different notebooks, and there are a few other notebooks. I mean, they're not really notebooks, but they're just like Python code, which kind of run through a different combination and just output you a best model with the submission file. I tried those submission files as well, but I didn't get a really much better score than what I already had. And one thing I really learned was that next time, pick your competition wisely. And yeah, and it's good to have some sort of domain specific competition, because then your personal interest is a little bit more, because this was purely working with data. It's nothing related to any domain. Like, you know, you're not learning about healthcare or anything or financial side of things. It's just purely overfitting. And I think I learned a lot about overfitting, but next time I'm not going to do a similar competition.
Yeah, wasn't Sepir at the beginning complaining about Kaggle and complaining about this basketball competition? He didn't understand basketball, didn't want to learn about basketball. And I was like, no, Sepir, that's why these competitions are so interesting. It's because the data does tell a story at the end, and you become invested into it. Totally.
Yeah, that's true. And yeah, and thanks a lot for you guys for letting me. Matt, I have a question for you. Matt,
shoot, but well, let's. Sorry, Mo. Is it about this competition? Because let's keep everything here, and then let's thank RJ, and then
no,
and then
about
you can
this
ask
one
after.
only.
Okay, cool.
So if you have a small data set like this, which is I've never seen before, what are the strategy you use in real life?
For me, I would probably just focus on. I mean, it's just so different depending on what the data is and what the task is, but. I would probably start with really simple models like RJ went over. I think that's a really good approach. And then a lot of data exploration. And only if, you know, I really learned something special about the data would I go beyond just a really simple model. Because I mean, what I've been specializing in is like kind of deep learning models, but with so few samples to go on, you just will not be able to avoid overfitting with models like that. So I think, yeah, the strategy here makes sense. It's just, I think it was so difficult because this data was curated to be hard to find patterns in, and that just made it almost too challenging to really know when you're learning something and know when you're doing it right or doing it wrong. So I think a simple approach will probably just do it for you, and a small data set you could probably do a really small project on and be done with it.
Thank you.
Any other thoughts on that? I'm certainly no expert with this sort of stuff. Like, I think other people might have some nice thoughts.
I'm no expert at all either, but I do feel like, yeah, the data set was kind of weird. If you have a real life data set, you would probably have some features that correlate with each other, and maybe you can do PCA or whatever. Yeah, this was a very typical problem.
I have a question. Hello, can you hear me?
Okay, yeah, we can hear you. Yep.
I have a question, just as a silly question. Is it possible to trade the test data with a portion of the training data and get more correlated data, and then get less training data and the test data, and then create more, like run the models on them?
I'm not sure I completely understand, but there are techniques
So
where
for example, let's say the test data was too small compared with the training data. So if you take a tiny portion that you move to the test data and not before you get into the training data, can that help you?
And use it as like a validation set to know how well you're doing. Yep. That's very commonly done. It's essentially it's done every time that you train a model. Is you hold out a set that you don't allow it to be trained on, right? So you can see how well the model is doing. But there are some cases where you can even be worried about overfitting to those unseen data. So you'll actually create 3 different sets. You'll have one set that you'll have for training, one set that you'll have for early stopping or kind of like a validation, and then another set for just kind of testing at the end to have a high confidence in. So definitely holding out data for developing algorithms is very used. Yeah.
Thank you.
Okay, I don't think we have any more questions, so why don't we call it here and give RJ a big thanks. It was pretty short notice, RJ, and you did a great job kind of jumping into it and learning about maybe too many models, but
Yeah.
I think with the competition, you were just trying to find something that would work, and unfortunately the competition was designed so that was not easy to do, but hopefully you got a lot of good experience. So let's all give RJ a round of applause and a big thanks. Can everybody unmute themselves? All right, and we'll go in 3, 2, 1.
Thanks, guys. Really appreciate it.
Good job, Harvey.